to environment and the workplaces as well. So although to control all these factors, there have been many other, but the most important thing is to detect the exact concentration or the quantity of those pollutant or hazardous material in the environment. For that, we developed a kind of device that we call it sensing device, or we call it gas sensors. So here I don't introduce about, because this has been, so among those gases, just I said about some of the gases are hydrogen sulfide gas, carbon oxide, carbon monoxide, carbon dioxide, nitrogen dioxide, or simple nitrogen gas, or sulfur dioxide, or sulfur gases, and then also VOCs. Of course, these all or other gases, they have adverse effect on human health as well. So for those, we use a kind of device, we call it gas sensors, or gas detector may be a word some people use, but those, when specifically we talk it in a technical term, for us detector sensors, they are different, and then they're in the intermediate also, that is called actuator. So a word directly defined for this all system is called sensor, actuators, and detectors. So here I will focus on the sensors only. The sensor, they basically only produce the interaction with the target gas and also the electrical signal of, just like simply define it, if I say it is taking the electrical signal into a physical input, a physical output. We can see, like, if you cannot see, if you cannot hear, you cannot smell, or you cannot be detected. So the focus is on few things, like we can prepare electrical or electrical skin, or maybe electrical hearing, just like I'm using here. And of course the microphone we are using, this is a microphone. If someone has a other problem, like if you remember the guy who is Stephen Hawking, the black hole concept guy, he has many problems, so he was using the 5 kind of sensor at the same time with a single chair, and one of them is electronic nose. So electronic nose, we call it as a gas sensor. Is there any problem?
No, sir.
Okay, so I can go on. So some of the catalytic gas sensors, they have different type. Of course, just I said, as there are different type of gas sensor, there have been diverse industry and the requirement. For example, the detection of alcohols, they are different. The detection of food poisoning, they are different kind of sensors. They can also be smelled as well. And also, like if we need detection of gases in case of radiations. So they have been gas sensors are based on 5 different reactions. One is catalytic bead reaction, infrared sensor or infrared reaction, then solid state of sensor, and then electrochemical and photoionic type of system. Here I will focus on the chemical type of sensor as well. But the one is type of catalytic bead type. It has 2 basically, electrochemical and chemical type of sensors. So what they do, they are prepared for the amplifier. Then we use a sensor array set of sensors. I will show it later. And then we test with the system, that is signal processing. And then we get a pattern of predefined recognition system, that we call it pattern recognition system. So the key parameter for the sensor system, there are 4 kind of system. We call it 4S system. One of them is the response. The other one is selectivity, then stability, and the temperature as well. A response defines the time or the reaction of the sensor with the adsorbed gas molecules on the surface of the sensor with the preset nanomaterial, like it may be MOS, or it may be MOF, or it may be magazine, any kind of material we are using. So sometimes it gives, after the interaction, it gives us some resistance, that we call it response. But also we have another thing, is that is recovery. I didn't mention here, recovery means the time in which it will come back to its original state. Then the selectivity. Before selectivity, I say about the stability and temperature. So stability, we will talk about the time in which, how long it can retain, or how many days or how many years it can be retained at the same time. The similar response for the whole system. But although, because due to the environmental factor, it has been very easily, it can be polluted. So the temperature is a temperature, we call it working temperature. It has many, for different materials and for different gases, the working temperature is different. And then finally the selectivity, because in the environment actually there are many gases. So we also use single gas detection, we also use multiple gas detection, and also the same time we use gas mixture system and then detect uh, the possible gases that can be detected. And one of the gas is always give a maximum response, that may be a reducing gas or maybe oxidizing gas, one of them it can be. So we call it the selectivity. So all these parameter I will later use a word keep term that will be optimal condition. So all these factors are when we define, we say this is optimal condition for some specific material for the specific sensor. So gone height of optimal working temperature, of course it is not good, we need a low temperature detection system. Then poor selectivity, of course this is also a problem one among the different materials. Specifically these are the problem with the metal oxide type of systems. And then the response is lower than poor recovery, especially at the room temperature systems. So you can see at the bottom we have one of the figure, this is our company or industrial commercial type of sensor we are already working on. And there are four basically steps: synthesis, processing, then structuring and property of that material. I will show this the bottom figure in three different sets. So three type of materials they have been used for generalize. If I have generalized here because my topic was on the diversity and or trends in the nanostructure for the specific these gas sensors. They can be 0 dimension, 1 dimension, 2 dimension, 3 dimension. So there may be question which one is the best. Of course all of them are the best one. They It depends upon the application where we want to utilize them. And then there may be another question where what is the main structure that can be utilized for which kind of specific direction. So this is not hit and dry. So it depends. If we need a low temperature, high response, then we see 3 dimensional. If we need a strong response for higher stability, then we use 2-dimensional structure. And if we want to use longer response with short recovery, that we use 0-dimensional type of structure. So these are all intermingled or intermixed structures we use at the same time for different applications. This all depends where we want to employ our prepared or fabricated gas sensors. So this one I have already described, so there is no need to go on for this one. Gas sensor, they can be used in a different field, for the biology, for the photo, for the electro, and we will discuss about the preparation and application and working mechanism as well. So first of all, I will give a brief idea about the different 3 testing systems. The first one is the older one, but this kind of testing system, it uses a voltage based systems. So you can see there on the right side, you can see there is a box. This we call it chamber. Inside the chamber, I have enlarged the image. If my cursor is moving, I can show you the and it is working. So here are fans. One is for exhaust, one is for evaporation. So and there is an array of sensor. You can see in the figure here. Inside there are about
'Sir, we cannot hear you.' I think Professor Shahid, the internet connection is creating some problem, so we will wait for a while. We may shift to our next speaker, Dr. Shabnam Javeen, currently serving as an associate research professor in physics department, University of Maryland, USA. She did her PhD from Kansas University, USA. She has expertise in particle physics, accelerator or detector particle identification, statistics, and MC simulation. So we may proceed to Dr. Shabnam Javeen to present her work with us.
Let me just share my screen.
Yes, please.
Can you see this?
Yes, it's going. Yes, we can see. Yes, Dr. Shabnam, we can see your screen. And
all right, very good. So, well, let me first say thank you for the nice introduction, and thank you for inviting me. I want to say special thanks to Professor Dr. Ftir for inviting me. I am not really sure why I am here because I am not a material scientist. And so I'll just share my new passion, which I'm hoping that all of you will find very interesting. And I will try to make connections to material science as I go. So I am going to talk about quantum computing, and I will share with you the latest in the field. In that sense, as I'm sure many of you know, it's an extremely new and very, very rapidly developing field. I will make material science connections where I can, and I'm hoping that some of the new people will pick up. So I am not sure how many here are students, but my talk particularly is geared towards the new incoming young blood and people who are looking at the horizons of science and new technologies. So why quantum computing? It's not long ago, just few decades ago, it turns out that there are technology, algorithms and technology that can exist that can make it very, very easy to hack our current very, very secure encryptions. For example, the RSA, as you know, it's based on prime factors. And to find those prime factors that make up a key is not easy. It is very, very hard computational problem. Classical computers cannot do it very, very quickly, which ensures the privacy of our data and any other place where we need encryption. But if we have quantum computers, which we are working on, these algorithms actually can do it exponentially faster, which means that once you have quantum computers, nothing is safe. That's an easy thing to infer from here. And this is the reason that everybody is suddenly, after this, suddenly jumping. So before I talk more about quantum computers, I do want to talk about quantum because all of us are physicists. And coming from that side, there are special qualities in quantum that I want to just highlight in a little bit. So I will just start from the beginning. And as I said, my talk is geared towards more young people and students. So I'm just taking the time to go through these simple details. So as everyone knows, we have only 4 fundamental forces, and all of those, everything else that we see is an artifact of these forces, whatever it is in biology or chemistry or any place else. And these forces and the phenomenon concerning them are explained by 2 basic theories. One is the general relativity, which explains essentially everything concerning the big galaxies and clusters of galaxies. And then standard model, which is based on quantum mechanics, is describing all the phenomenon concerning atomic and nuclear forces. And by the end of 19th century, early 20th century, we were already essentially finished setting up the physics of the world around us, the visible world around us. And the picture was quite nice. We could solve almost every problem that physical world was throwing at us. And to the point that people at that time started saying that, well, we already know how to solve everything. The only thing we need to do is keep repeating our experiments and make them more and more precise. And it wasn't such a strange statement, except there were only a few things. For example, black body radiation wasn't understood, and people weren't that worried about it. But it turns out that in order to understand those things, we actually ended up having 2 revolutions in physics. And those revolutions, in fact, they did not change the way we look at physics, but they also changed the way we look at the universe around us in terms of space and time, or philosophical questions like free will. And those, as you know, those revolutions, one was the general relativity in 1905, and the other one was quantum mechanics, which started with the paper by Planck in 1895. And as you know, Einstein's Nobel Prize paper was actually the first one which gave us the idea of the actual quantum of energy. And this is a funny thing because Einstein got Nobel Prize for this paper, but then the rest of his life, he actually tried to fight the ideas of quantum that he actually fathered. And so quantum mechanics today that we have, there are many interpretations. And this is again a strange thing about quantum mechanics, that the theory, that standard model is such an extremely successful theory based on quantum mechanics. But the core ideas, we still are struggling to interpret them, what exactly they mean. For example, the most common and famous one is Copenhagen Interpretation. But that interpretation tells us that there is probability involved. There are superpositions of states, like the Schrödinger's cat, which can be alive or dead at the same time. And there is something called entanglement. All of these things have no classical counterparts. And this is what makes quantum mechanics so special. It's kind of strange, fascinating, but somehow it works. And we are still struggling to understand these things. But again, as I said, and as you know, this thing works extremely beautifully. And just to remind us, Einstein and Bohr, for example, had a long fight between themselves. And Einstein's famous quote is, God does not play dice, is in fact coming through this whole fight. his dismay over this uncertainty and indeterminism that comes out of quantum mechanics. And in fact, when he was writing this EPR paper, one of the things that came out in the newspaper, the words that were used were system of delusion for quantum mechanics and the concepts. But now we see this year, a Nobel Prize is given to Alain Aspect. And I'm sure you all know Alain Aspect did the experiment in the 80s, which proved the experiment that on Bell's theorem, which essentially proved experimentally that quantum mechanics is the way of the universe. Bell's theorem already proved that theoretically and almost put the Bohr and Einstein feud to rest, but Aspect actually proved it. And if you look at the Nobel Prize Committee's wording, they say that this is for establishing the violation of Bell inequalities and pioneering quantum information science. So again, here we see that this is a nod to this revolution, quantum computing, that is really, really flourishing at this time. And as I said, quantum mechanics, we do not understand it even today. And as you know, I think there is nobody famous in physics who actually feels comfortable about it, including Feynman, who devised quantum electrodynamics, Gell-Mann, who started QCD, and Bohr himself. But that does not stop us from using it, and we have been successfully using it as in terms of, for example, standard model. I mean, everything that is based on quantum mechanics works very nicely. Quantum computing in itself essentially started with Feynman, where his famous quote is that, damn it, if you want to make a simulation of nature, since nature is quantum mechanical, you have to have a quantum mechanical computer. And since then, Feynman gave ideas about quantum computers as well. And since then, today we are at a point that quantum computers, everyone who wants to bet on a future technology is actually putting money on quantum computing. So it's governmental level as well as the private sectors, where we are now talking about billions, and soon it's going to go to trillions of dollars that are being thrown at this industry, both experimental and theoretical work. And you will see we are quite far in that sense. So before I get to the actual quantum computers, let me just give you an idea of what is the difference between classical and quantum computers. So in classical computers, we say a bit, or the data is used in terms of bytes. So a bit is nothing, it is just a 0 and 1 state. So current on is 1 and current off is 0. That's all. And 8 bits make 1 byte. And 8 bits means you can have zeros or ones or zeros or ones, and you can put information in those zeros and ones. And that's how you can manipulate it through the value of current. You can flip a bit and you can write something in computer's memory. And for example, if you have 8 bits, that means you can have 1, 1, 1, 0, 0, 0. These 8 numbers you can have there. And in those 8 numbers, you can have 256 variations of those numbers. But the state at one single time is just 1. You can write one kind of 100100 number. Only one state is possible in one given time. On the other hand, if you look at a qubit, it's not just 0 and 1. It's a quantum mechanical 2-level system. And we know that quantum mechanical systems can exist in a superposition. So the superposition means that any state, it's a superposition of or simultaneous 0 and 1. So your 1 bit is not just 0 or 1. It can be 0, 1. And when you have multiple bits, you can have this 2 to the power n dimensionality to these states. So what does that mean? It means, for example, if you have 80 bits, you still have one state that you can store in one time, or one state that you can look at one time. But in quantum computers, if you have 80 qubits, that means you have 2 to the power 80 states. And if you write down that number, in its actual form, the number is actually bigger than the number of atoms that are in the visible universe. We can estimate that. It's such a huge place where you can store such a huge number of information and the number of states that's available to us in terms of qubits. It's astronomically better than anything else we have seen so far in terms of computing power. And that is what makes quantum computers so precious. Now, I want to give you some idea how actually quantum computer works. And when we say that quantum computers are very, very fast, what does that actually mean? And here it's a small example that if you have 2 points and you want to go to one point from point A to point B, and let's say there are 8 different paths to get there, and you want to know what the shortest path is, the worst case scenario is that if you do not have any other information, you will actually have to walk every single path one after the other and then figure out which one is the shortest path. And that means that you have to have n operations done before you can do this, you can make this decision. On the other hand, if you have a quantum computer, you do not have to do this one by one. This whole thing is one state. You can look at it and you can readily pick the one that is the shortest. And here is a small example. And the reason I have this slide is just to show you that even though we say quantum mechanics is we do not understand, or we interpret, there are different interpretations, or we are still debating what it means. There is probability and there is indeterminism and there is entanglement. But in the end, it is all mathematics. So we know the rules the universe is following. They all come down to some sets of mathematics. For example, in this case, we are talking about Hilbert space. And those mathematics, in this case especially, it's just linear algebra and matrix multiplication. And once we do that, everything falls into place very, very nicely. And when we go and we actually measure those things in quantum computers, we actually get what we can prove from this mathematics. So even if we do not understand quantum mechanics, we know that universe is speaking in terms of this mathematics, and that mathematics works extremely beautifully. So in this case, if you have, let's say, 8, there is a set, let's say 8 names. You are on Google, and Google comprises of, someone trying to talk to me? Okay, sorry. All right. So, so if you have a set of 8 names and you want to search, and this is just an example, we can search on Google for billions of things, and we can think of it as a small example of that. So out of 8 names, you want to search for one name. This specific Grover's algorithm, which is essentially mathematics, it will work in a way that it will create, we have this state of 3 qubits, which means we now have a state with 8 elements. All of those 8 names are encoded in those states, and your algorithm actually can go in, and if you can see my cursor, it can look at all of those 8 states at the same time rather than going through them one by one like a path. And it can look at the one it is searching for, and it can flip it. So the amplitude is now negative, and all we have to do is now amplify that amplitude. So rather than doing n times or n operations, you just did one operation to flip and the other operation to amplify. And that's how you get the exponentially faster algorithm, because in quantum mechanics, you don't have to search one by one. Everything is right in front of you in terms of those states, because quantum mechanical system can hold that many states at one time. And this is where superposition and entanglement comes into play. And this is what will make the thing that I said in the beginning, that cracking the code or breaking the encryption, like finding factors, prime factors for encryption keys, that will become much, much faster, much, much easier. So in terms of development, in terms of physical development, and the one that you might be more interested in terms of material science, this is an area where a lot of progress has already been made and people are still working on. The two that we are using are superconducting based quantum computers and trapped ion. And these are the ones that I'm going to talk a little bit about. I don't know how much time I have now. Is anyone keeping track? I don't remember when I started.
Madam, you have 10 minutes now.
All right. Okay, thank you. All right. So ion trapped qubits. So the way it works is the way the name is. You take an ion and you have one single electron in the valence shell. And once you have this one electron, it can you can manipulate the spin of this electron in a way that it can be flipped. And since it is an electron spin, you can flip it in a way that you can flip it all the way up or down, or it can be in a mixture state. And this is what makes a qubit, where you can have a 0 state, a 1 state, up or down spin, or anything in between, which is combination of the two or the superposition of the two. And this makes a qubit with one ion. And the beauty of this system is that it is natural, and the coherence time, which is extremely important parameter for quantum computers, is very large. So that makes it very nice. So starting from the upper left corner, this is one atom. This is literally a picture of one atom trapped between these electrodes. And here you can see the chip on which this ion is trapped. And we are talking about a centimeter length. Here we are talking about, this is a blown up version, 4 qubits. And these qubits are like microns apart. This tiny chip is housed in this vacuum chamber. And then the whole thing is manipulated through these lasers and is read out through these photo readers. So this is how an ion trapped quantum computer or processor essentially is made. This is the one we have at UMD. Again, this is the same kind of chip. Here is the housing chamber. And here you can see a whole jungle of these lasers. And this is where a lot of material science comes into play, because making sure that all of this system works and the connectivity and the material, everything fits together and the noise is reduced in operations is going to be the key in order to get a commercial computer, which we don't have at this point. The other computer that is very popular, and people like Google and IBM, they have a lot of them. They are working on these constantly. And these, you can see that they are essentially superconducting. They are called superconducting. So that means that they require a superconducting, like a freezer, where you can have temperatures up to millikelvins, where you can house your chips. And the way that works is that this is essentially a superconducting coil, 2 wafers of superconducting material, and then you have a capacitor of superconducting material. You essentially are making an LC circuit. And once you have that LC circuit and it has a resonance, you can manipulate that resonance into levels. And once you have those levels, you can use it as a quantum entity with quantum levels.
So,
is there a question?
No, ma'am, you please continue.
All right. So here we have, this is one of the latest things. So we have here 80 qubit ion trapped chip. You can see the chip, and this is a blown up version of, this is the actual ions trapped there are 80 ions, and the distance between every single ion is like 5 microns. And you can see the precision of this thing, and that it can hold 80 qubits or 80 ions in this state. This whole thing is like 1 centimeter. So it's an essentially very, very tiny thing, but the precision is extremely nice, and the coherence time is extremely large. So the technology has already developed quite a bit. Last year, IBM Quantum, they unveiled their 127 qubit quantum processor. So they are also getting very, very close to having sort of a commercial thing out. All right, so this brings me to the conclusion. I just wanted to share with you that the quantum computing, this is the new thing. Almost everywhere it is a new thing, and at UMD it is a big, it is turning into a big thing. We are going to be using this for LHC data analysis, hopefully very soon. It's here to stay, hopefully, and scalability at this point is very important. And this is where you guys will come in, because having the materials that work with the precision and without defects so that we don't have noise, that is going to be the key in scalability here. And yeah, I mean, and material science from the other side, once we have the quantum computers, you guys will also benefit, because you can simulate. It's very hard to, what I understand, is very hard to simulate new materials, but the quantum computers are going to make it extremely easy. And so any industry that benefits from those kind of materials will actually benefit from these computers. All right, this is all that I had to talk about. Thank you.
Thank you, ma'am. Very beautifully explained the very interesting topic, though it's very far away, but you explained it very beautifully, the quantum computing. The room is open for questions. Okay, thank you, ma'am. If no question, then we can move to our first speaker again, and apologize for the signal issues and everything. Professor Shahid, you may continue.
Yes, please let me open the share.
Dr. Shabnam, you have to stop the sharing, please.
Yeah, let me do that.
Yeah.
Okay, thank you so much. And sorry for inconveniences that happened due to the internet problem here. Because I was, yeah, thank you. Can you see my screen now?
Yes, we can see your screen.
So we were talking about the testing system. First, I add one thing, because just now I thank for the Dr. Shabnam. She was talking on the computing. Also, we also use such kind of system. We called it as a server here, and use a DFT simulation system that is based on the WASP software. And the similar thing is also done here on the one I showed before, NDIR type of sensor systems. So we also use such system as well. So going on, I was talking about the first type of sensor system that is based on chip-based sensor system. So three of the sensor system will be chip-based sensor system. Here we use an array of sensors that has been shown on the right side, on the bottom in the chamber, and the chamber has been enlarged and zoomed. On the left-hand side, you can see there have been temperature sensor that just for detection of for the setting of the temperature, then evaporator, and for the low and high voltage setting, and then the fan switches as well. And the system, how to integrate or how to fabricate the sensor is shown on the bottom. You can see on the right side as well. Specifically, see in figure C first. So this is a pedestal sensor pedestal we use. There are 6 sockets on it, and we pass, first we paste aluminum electrode on it, and then we pass a nickel chromium heater inside the electrode and engraved on the surface of the sensor pedestal as shown in figure D, and the circuit is shown here as also on the just beside the figure D. A single circuit totally engraved and compact made is shown in the highlighted one. And next one is about a type of CGTP system. Now we are using these three type of system here as well. This type of system can detect, can use one microprobe system. They have been used on the surface of the sensor, but although this system is more efficient and a very small chip is used, maybe 100 of chips can be imprinted on one nail. So this is very small, like a kind of nano sensor as well. So as you know, there have been many small kind of devices or integrated circuits pasted on or put on the microboard or the chipboard of the computer. So this is the one how it comes from the backward technology. But because recently we are working on developing a sensor for a mobile company, they want to directly embed their sensor that can detect the gas directly rather than taking data from online system. Like some companies they take data from the Google, some companies they take from the data iOS and other sources, so then they update into the system. So now it has been already developed so that the direct detection can be done on the mobile as well. So this is one of the system I have shown here. You can see in figure D there have been 4 sensor arrays. Of course, they are of very small size. I have put the micro pictures of there here. So this is the measuring system is shown here. So these 3 systems we have been using here since maybe more than 5 or 6 years in my lab, and my students are working on it. So for developing of the gas sensor system. So this is the detection of particle molecule, how it is detected. It is totally about the physics, this is clear physics from the absorption to scattering, and then from the anti-Stokes or the Stokes-Raman scattering. So there have been 2 types of course, all of you know and more aware than me, because you are of course elder than me and know about these kind of rotation. So, but actually these kind of rotation, they give some excitation or de-excitation of energy. So from where we detect our exact molecule system, how much energy is liberated or how much energy is absorbed. So we can detect each electron or single molecule very easily, but that's all based on the spectroscopy or those kind of machine that we are using here. The basic theme is also taken from the physics, also from the quantum mechanics as well. And 2 kind of gases, basically for oxidizing gases, they have tendency to accept electrons, among them oxygen, nitrogen oxide gas, and then carbon dioxide gas. And they accept electron from the surface of material and absorb more quickly with the sensor surface under the normal temperature condition, like it is less than 50 or under the 100 Celsius centigrade. This, of course, the absorption is very important. That can be increased by increasing the temperature and the size of the particle, or also with the doping. Mostly, just for here, I just say in this kind of devices, the important thing is to change resistance and keep the resistance as low as possible. And for under the 100 Celsius centigrade, there is a release of 1 electron, or it can accept 1 electron in case of oxidizing gases. And also above 200 or more than 200, it can accept 2 or electron or more than 2 electron. So it all is about the interaction of gas molecules and also the material that is coated on the surface of the sensor. If the gas is redox or the reaction is redox, so the process is totally converse type of process system. So I will talk about the 2D magazine material here. Magazine material, they have different sets. They come from basically aluminum, silicon, phosphorus, gallium, germanium, arsenic, and so on. And then the max material, A come for the SCTI, CR, and so on. So we call it a max material, and their intermediate material is either fluorine or oxygen, carbon, or nitrogen. So titanium is the basic material as well that has been used in the magazine kind of material. For the heterostructure, if we want to develop a heterostructure among those material, I have just put one table to show here which kind of material they can be used for what kind of gases and their selectivity, their sensitivity, their response, and how much concentration we can detect at what temperature. So you can see, for example, SN, MOS2, and so on, WS2, MOSE, and MOTE. All these material, they show maximum response at room temperature on the third, fourth column. And also for, if we go down for graphene, graphene related material like graphene and molybdenum disulfide and graphene like aluminium nanoparticles at composite made with all the other up materials. So they also show response, but the temperature increases very, like it can go up to 150. So this temperature is mostly considered as high temperature, but for some application, temperature can go up to 400 to 500. Like for example, if we need to go beyond the space, and maybe some places it is under freeze, more less than freezing, like many minus Fahrenheit, or maybe some places the temperature is much higher. So it all depends where we want to utilize these kind of materials. So the maximum material they can be, they have been used for specifically for two-dimensional material have been shown here. The maximum response you can see is 300 response, that is for MOTE. Although this response is not that much higher, because one of my students recently, he got a response that is more than 6,000, and that is at room temperature also. This is ideal, but I haven't shown here. I will show maybe in some future time. I will show, because that have not been published yet. So maybe I cannot put it that here. So these two-dimensional material, they have intercalation. They have ion species. They have ionic or inorganic molecules type of system. They have been used in optical, magnetic, thermal, catalytic, energy storage, transparent, and so on, many application as well. So what's the basic theme or basic idea of using those such kind of material is their work function. This is most important, because as a physician, you also know that when we use some material, or when we are talking about, we always talk about the band structure system. We talk about this is formation band, this is like forbidden gap, this is valence band and conduction band, and so on. So these energy bands, like in our masters, maybe we have studied about the perturbation theory as well, like and also the wave function as well. So those all are taken from where they have been, those ideas come basically from the heterostructure, or kind of those places where there is experimental based. For the, if we talk about the band alignment of the metal semiconducting heterostructure, because what we read is not all about the metal materials, not about the metal oxide material, not all about the insulated material. The story is different for different materials, because mostly it has been discussed for hydrogen or sodium type of material. Those have a single valence type of atoms. The alignment of band structure or the band of the metal semiconductor heterostructure should satisfy the Schottky-Mott rule, in which the ohmic contact is formed. Mostly the ohmic contact is formed at the interface. That is according to the work function. And work function means work function for the material, and also for the semiconductor. It depends on the type of semiconducting material as well. And then if we superficially, we talk when work function of the material is greater than the work function of the semiconducting system, that means there will be free electron near the interface, and they will be transferred to the side of semiconductor, and they will form a ohmic contact between the metal and a type of semiconductor. So semiconductor, you know, there are two types, N type and P type. So first, this ohmic contact, ohmic type of contact, the resistance contact will be for when the work function of material is greater than the work function of Schottky one, that will be for N type. And if it is for the P type semiconductor, it will form another kind of contact, and the electron transfer will be between the semiconductor and the metal. They will continue until the Fermi level reaches. So Fermi level means it will go to the about 0 electron volt of energy, and there will be thermal equilibrium for those, and there will be no further conduction of those. So we will say that our most of the material, they become like near about the insulator type of systems. And interface, I already talked about this. Interface has been shown. This band alignment, they chart transfer behavior in two-dimensional heterostructure materials, semiconductor type of SSC, semiconductor material, and semiconductor insulate heterostructure material as well. So this all story I have talked about. You can see if phi m is less than or greater than phi s, it will be ohmic contact between metal and semiconductor. It will be n-type semiconductor. If it is Schottky contact between metal and then it will be p-type of semiconductor. So this schematic is also shown energy band diagram of molybdenum sulfide for p-n heterojunction based sensor that is under developing under the UV irradiation, because we can also illuminate or excite our surface electron using different light like UV lights. We can also use different other lights to accelerate or excite those surface electron if they have not been accelerated or they do not show any resistance or any conduction through the testing system. So we use a force, a pressure to increase their kinetic energy as well. So this is the first one we have recently, like last year, maybe we are published in Applied Surface Sciences, that was enhanced as NO2 gas sensing performance of two-dimensional magazine, this Ti3C2 and titanium oxide composite by in situ formation of Schottky barrier. These are typical figure, for example, XRD, XPS, and other also illuminated like large as in convoluted type of XS figures. So you can see if some of you have material background, so maybe they can know easily these are XRD peaks have been well aligned with the what we have prepared as well. So I just go to the material formation. This is a scanning electron microscope, transmission electron microscope, images at different different sample for different sample prepared at different temperature. For example, you can see in figure A, this is simple max material, a simple magazine material, but then we dope with the titanium oxide. You can see in figure B, C, D, E, and F, they have been embedded very efficiently, very prominently, and uniform as well. And then they produce a heterojunction between Ti3C and TiO2. And in figure A1 to A2, A3, B1, B2, and B3, these have been like TEM or transmission electron microscope and higher resolution TM figures. And also SAED is shown in A4 and B4 as well. They show very relevancy with our as prepared product that have been prepared on different temperature from room temperature to 220. This is the synthesis temperature, but we will next go up to the conduction band. We are also simulated the conduction band, also got the conduction, energy band also simulated, and as well also we got experimental band gap diagram from both the set of equations. So also we did the gas sensing. This is a gas sensing curves for those as prepared material. You can see 180 or about 220, they show the maximum response for the NO2 gas. And we have tested like 4 gases: nitrogen dioxide, sulfur dioxide, NH3, and carbon monoxide. So similarly, we see maximum response was gained at 180 centigrade for nitrogen gas. And you can see if the air is purged, air is input for the first time, then the resistance goes up, then and gradually decreases as well. So we can see there is a time of recovery and time of response in figure A down on the bottom. The response time and the recovery time are low. They are very large, 300 second and 275 second. As I said in initial my two slides, because all parameters cannot be satisfied at the same time. So we try to control some parameters and then get specific output for specific sample. And in figures B, you can see it has been decreased to 150 second to 72 second. Of course, this recovery time is very good, not that bad. Although the recent sample we have achieved the recovery time is about 10 seconds. So that is very sharp recovery time for that one. And also we tested our sample for the different humidity, because these gas sensors, they have been affected badly with the humidity effect from because they absorb oxygen on the surface of the molecule on the gas sensor, and during the experiment, but after when we fabricate the device, of course, the environmental factor, they affect very intensively on the whole. And this is a simulation we have done on both. We have compared also the simulation results and also the experimental results. You can see both in figure E and F. They show a maximum response even for the simulated one, and also, of course, experimental, because that has been experimentally proved, and it gives a very good absorption energy, and also ultimately high response for nitrogen dioxide gas. And this already, because this is a typical curves just for the like supporting information or supporting data for different concentration have been tested for different temperature, different parameters, and linear response has been seen. Also, it shows a maximum linear response of 0.9, and that is more than ideal. So because it is very important to find detection limit as well. So here in this case, our detection limit was about 3 ppb for nitrogen dioxide gas. And for the next is for SNO2. मैं presentation कर रहा हूँ, 10 minute बाद आइएगा. After 10 minutes, Jesse, I'm online. And the other one is on the SNO2 with the magazine material. So this material for room temperature sensing, and the composition is with the tin oxide and titanium carbide composite, controlling the facet. We try to control facet. You can see in figure on the right side. Magazine material is on the as a template, and then there have been polyhedral type of shape that have been embedded, or they have been floated on the outside of the max material. So typical figure also have been shown here for the Schottky barrier, and also for TEM and HRTM as well, and for the simulation one, that one for quantum effect as well. And you can see here figures, it is detailed structure for different samples with different construction. They show ultimate uniform nano structure for their synthesis process at the initial stage. And at the bottom also XRD figure has been shown as well. And secondly, also again XPS typical XRD figure with the different facets like 2 to 1 and other faces, because we focused on 110 and also 2 to 1 face, that because it is multifaceted, so we had a try to use double face of a single nanomaterial to get the multiple exposure of the gas molecule interaction with the fabricated material. So maybe it was thought that it could get a better response than the previous one. So it happened as well. It has given a better response than the previous one. You can see in figure A and also in figure F. It shows again maximum response for nitrogen dioxide gas, and the response was 1.6. This, of course, the result looks very small, but this is the percentage response. That means the response was about 160, and this response is also very ideal. Different concentration and different curves has been shown in figure. On the left hand is the figure A, that is also for humidity, but this sample was affected by humidity due to the usage of SNO2, because SNO2, zinc oxide, tin oxide, tungsten oxide, and other these single metal oxide, they are easily affected by the environmental factors. When the temperature is higher or lower, they easily decrease their response with the gradual increase of humidity. And the Schottky barrier is of course is shown here. They show conduction of near the semiconducting type of material 2.41, and also afterwards, after the contact, they also show a very ideal type of conduction for the whole contact of the system. So just these are the publication, maybe no need to show. I'm working also for, this is the oldest one, because I'm working it in general as an editor almost for all kind of journals elsewhere, Hindawi, Springer, and so on. If you have any condition, any help needed, I can help for those things as well. And thank you for all. If you have any question, you are welcome to ask, please.
Thank you, Sir Shahid, Professor Shahid. So nice of you for such a interesting work, for presenting such an interesting work to us. Any questions from audience? Okay, if no question, then we will move to our next speaker. He's with us. Professor Dr. Muhammad Yasin from the Department of Physics, University of Agriculture, Faisalabad. He did his PhD in nanofluids and thin films from the University of Technology, Petronas, UTP, Malaysia, and MPhil degree in plasma processing from Quaid-e-Azam University, Islamabad. And he have also worked as postdoc fellow with the director of hybrid energy system research at UTP. He has published more than 450 publications, 200 journal publications with an impact factor of 450, and also involved in publishing the books and book chapter almost 24. He has been a member of supervisory committee of 105 campus students and 12 PhD students. He has presented his research work in more than 55 national, and international scientific events. Please, Dr. Yasin, share your work with us.
Yeah, thank you very much. Can you hear me, please?
Yes, we can hear you and we can see your screen also.
Thank you very much for a nice introduction, and let me thank you and all the organizing team for organizing this wonderful event. I'm Dr. Muhammad Yasin from Department of Physics, University of Agriculture, Faisalabad. And today I'm going to present on the waste management, especially the plastic waste into variable production. For example, the production of the nanomaterials, and in nanomaterials, my focus is on carbon nanotubes. So the layout of the the layout includes what are the good and the bad and the ugly things about the plastic waste in the Pakistan, and what are the mechanism of microwave assisted pyrolysis for production of valuable products, and what are our achievables, and the catalytic microwave pyrolysis mechanism involved in the production of the valuable products. And finally, the products that we get include the oil, gas, and solid residue. And then we conducted the analysis of these products to find out the industrial applications, and finally the concluding remarks. Okay, the waste plastic are counted as non-biodegradable materials, and the reason for multiple environmental and health issues. These materials are not only harmful for humans but also for aquatic and wildlife that mistakenly eat these materials. So plastics are widely used materials in all over the world due to their high strength weight ratio and low cost. However, the economic development of the world is also being affected by the plastic waste. And the management of waste materials is a growing challenge with adversely impacting the environment. So roughly more than 6 billion of plastic waste is produced worldwide, and out of this bulk amount of the waste, only 9% is recycled and 60% is dumped or landfilled, and the rest is burned. And it is estimated that in 2025, these figures can double, means from 6 billion tons to it can reach up to the 12 billion tons. So this shows the intensity of the problem we are going to face in near future. Since it is difficult to process such a huge stock of plastic, a large portion of waste plastic from developing and underdeveloping countries is burned due to lack of resources and planning and rapidly shrinking landfill capacity. The burning of plastic along with the fossil fuels is putting on risk the human health, marine life, and the environment. So here, Pakistan is producing 3.3 million tons of plastic waste every year, and most of it ends in landfills, unmanaged dumping, and also it flow into the lands and the water bodies across the countries. So it is causing the major concerns like the environmental pollution, including water and air pollution, and deteriorating the potable water quality, and also creating the health issues and putting the wildlife on danger. So if we pile up this 3.3 million tons that of plastic waste that Pakistan produces in a single year, we can reach to the height of 16,500 meters, and which is the twice the height of the second highest mountain in the world, I mean the K2. So this data is actually extracted from United Nations Development Program conducted in March 2020 in the Pakistan. So you can imagine the intensity of the issue we are going to face in future. Means if we produce plastic in 1 year and we pile up it, it can double the height of the K2, which is the highest peak of Pakistan. So here are the major contributor, the packaging, industrial packaging and household item packaging, also the food products packaging. It contributes 64% plastic waste, and then it followed by the automobile industry, which contributes about 14%, and other are also the major sources, for example, agriculture and construction industry, electronics, etc. So the major types of the plastic waste are the polypropylene, polyethylene, high density polyethylene, low density polyethylene, polystyrene, polyvinyl chloride, and PET. These are the major type of plastic waste, and among them, high density and low density are the most important plastics, because they produce large more amount of the plastic waste as compared to the others. So what are actually the problem? In Pakistan, we waste the plastic bags after a single time use. For that, the government is putting some ban in some cities to replace the plastic bags with the degradable bags. But the remaining waste is being dumped, including refuse plastic, and some of the plastic is being recycled, which has economical value, and it is recycled through mechanical methods. And this recycled plastic comes from the garbage pickers who did not have any data to analyze and also to make a record for future measurements. What are the patterns and trends currently in our country? Because plastic is a cheap, easy to buy, it is a durable and freely available. So it is replacing the steel and the iron. So the people are focusing more on this aspect as compared to steel and plastic due to high cost. But at the same time, there is no implementation of environmental policies and the regulations, and no formal waste recycling and reduction programs. Therefore, the structure is like that. The local system does not develop policies and programs which can check the growth of the plastic waste and the possible remediation for that. What are the mental approach of a common Pakistani? Means we think success means buying more stuff, and plastic is the cheap to buy. So once we use it, why we should care about it? It's government responsibility to manage the waste. So these are actually our approaches which we need to change. For that, we have a clear political agenda setting and civic engagement. Means we have to make the programs for the education of the Pakistani and the public to show their responsibility and change their behavior towards the waste management. We have clear targeted missions, and we have innovation across the sectors, and then we have experimentation to reduce the new approaches to deal with this issue. So we have to be creative and effective plastic economy. We should reduce the leakages of plastics into the natural system and also address the behaviors of the people towards this common issue. For that, we have to develop a supply chain. We have to change our behaviors. We need to adapt new policies. We need to collect proper data and use the novel tools like artificial intelligence to create the data, and also how we can find the solution to manage these waste problems. We need to think about the alternative products. we have to consider it an important part of economy, and also when you consider anything as a part of economy, we have to know drawbacks of this aspect as well. And at the end, all this enters into the waste management. And once we talk about the waste management, other than burning and landfilling, people normally talking about the plastic, the conversion of plastic into the fuel, and the rest is empty. There are a lot of the gaps which have the question marks. So having this gap in our mind, we have the objective to address the plastic waste management issue through microwave assisted catalytic pyrolysis and the production of the liquid gases, fuel, and valuable carbon residue in the form of carbon nanotubes, which have many multiple novel applications. And creation of the and characterization of the obtained products are possible industrial scale applications. So we adopted a microwave heating mechanism for the pyrolysis or conversion of plastic waste into valuable products like liquid combustible gases and the carbon nanotubes. For that, the waste plastic is since waste plastic is a renewable source because synthetic plastics are hydrogen-rich feedstock. The hydrogen content of plastic varies from 8 to 14%. However, due to low cost of the virgin plastic, recycling of different forms of plastic is not economically appealing. So alternatively, waste plastic can be valorized into combustible gases, high-value carbon, and chemical and monomers. So it is also possible to convert plastic waste into high-value carbon and hydrogen through microwave heating, which is quite different from the conventional heating, because in this process, a heat scepter is used to absorb the energy from the microwaves and convert this energy into the heat which goes to the plastic. Because plastic is an insulator, it does not directly absorb the heat from the microwaves. So microwave pyrolysis based on the principle of electromagnetic heating. Microwave reactor functions at a frequency of 2450 megahertz with the microwave power range of 3 to 60 kilowatt and having the microwave wavelength lower than the 1 meter. So generally a heat susceptor and catalyst is used to break long chain hydrocarbons of raw materials, especially the plastic waste, into short chain molecules through rapid microwave heating in the temperature range of 300 to 600, which is highly efficient method and give us selectivity on the product. So in microwave heating, the heating start from the core of the material and the heating expand towards the surface, unlike the conventional heating where heating start from the surface and penetrate towards the core. Therefore, the microwave heating has merits over the many other methods like the conventional pyrolysis. It is an energetic coupling process between heat susceptor and the plastic waste. It is an internally heating process. It is rapid and volumetric process. It gives us highly selectivity and depends upon the dielectric properties of the heat susceptor to be used for the transfer of energy from microwave to the plastic. On the other hand, the conventional heating is conduction based on conduction or convection process. It is externally heating process. It is slow as compared to the microwaves. It is superficial and non-selective. It is difficult to control this process as compared to the microwave heating process. So here is the mechanism of microwave heating of the plastic waste and production of the valuable products. When microwave interacts with the dielectric material or heat susceptor, it forms dipoles. Dipole polarization occurs in the direction of the electric field, and since the electric field changes polarity over time, so these dipole rotates and also shrink and expand. So there is a friction. This friction produces the heat. This heat interacts with the plastic and break the longer chain plastic molecules into the shorter chain molecules, into hydrogen, into carbon dioxide, carbon monoxide, and liquid fuels, being gasoline quality. Generally, this quality of the fuels are produced through this, and along with it gives us the residue. generally the residue is the char, which is also an unwanted material, and it is a waste. It also have environmental hazards. So our focus is that the residue should not be a char, it should be a something like the structured carbon, and focus here is the carbon nanotubes. So we choose the polypropylene and high density polyethylene, two materials. We use them in pure form and also mix them together. We use a heat susceptor, activated carbon as a heat susceptor, and we use zeolite as a catalyst. We mix these materials in appropriate proportion and then expose to the microwaves, and we obtain the carbon nanotubes. We obtain the liquid oil, and also we obtain hydrogen, methane, carbon dioxide, and carbon monoxide in this process. So this is the summary of the method and materials we use. As I mentioned, we use zeolite, ZSM5 catalyst type, and activated carbon because it is a best material. It has high dielectric loss factor as compared to the other materials. So it is the best intermediate to transfer the heat from microwave to the plastic. So this is the schematic of the experimental setup. It consists of a microwave source. This microwave source is shielded with a pyrolysis chamber, and it has a ceramic fiber block on which we put the feedstock, and then there is a microwave guide. That waveguide focuses the microwaves onto the feedstock, and this feedstock converts into the liquid and also the liquid and vapors and also the gases. So we use the nitrogen as a carrier gas. This nitrogen carries the vapors and the gas towards the condensers and the cold traps, and then we collect this gas in the sampling bags, and also use a gas sampler to check the composition of the gas we produce in this process. Okay, the important thing before we start this process, we have to know that in what temperature range the plastic can be effectively converted into the valuable products. For that, we conducted thermogravimetric analysis and check the initial temperature and oxidation temperature of the plastics. So we observed that in thermogravimetric analysis, the initial degradation of the material or the weight loss starts about 300 degrees Celsius, and oxidation temperature starts roughly around 500 to 600 degrees Celsius. It means we have to pyrolyze, or means the deconstruction of the plastic should be done between 300 to 600 degrees centigrade for effectively conversion of the plastic into the valuable products and the residue. So here we use the three types of the plastic, means high density polyethylene, PP, and the mixture of PP and HDPE. We use the sodium ZSM5 catalyst. We use activated carbon as a heat susceptor. Then we keep the plastic to catalyst ratio as a 110. We use micro power of 1 kilowatt, and the temperature of the process was kept constant at 450 degrees Celsius, and the mass of the feedstock was fixed at 550 grams. Then we check the conversion efficiency at 450 degrees Celsius. 80% HDP converted into the liquid and gases, and the rest was 20%, which is the solid product. Similarly, under the same condition, PP change, 80% show change into the liquid and the gases, and 12% was the residue, which we anticipate that it would be the structured carbon, I mean the carbon nanotubes. And later on, we characterize this material to check that either this is a char amorphous material, amorphous carbon, or a structured carbon in the form of carbon nanotubes. Similarly, the mixture of these two plastics produced 84% gas and the liquid, and 60% was the residue. So these findings suggest that if we want to produce the liquid, our focus is on the liquid and the solid product. we should prefer HDPE material in the microwave pyrolysis. And if our focus is on the production of the gases, we should choose the PP because it gives us 40% of the gas, which is much higher as compared to the others. And the HDP give us the 20% solar residue, which is much higher as compared to the PP, pure PP, and its mixture with HDPE. So then the gases we get during this process, we analyze these gases to check its composition, and we find that this gas consists of 81.3% hydrogen when HDP was used as a feedstock, and 78.4% hydrogen when PP was used as a feedstock. And this figure slightly improved to 80.8% when we use a mixture of HDP and PP. It shows that the hydrogen content was almost similar in all three cases. However, the HDP shows slightly higher content, hydrogen content, as compared to the pure PP and its composition and its mixture with HDP. Okay. So the oil product was a thick wax form. So we performed FTIR analysis of this liquid product to check what kind of compounds can be in this product. So FTIR analysis shows that at higher wave numbers, we have aromatic carbon hydrogen stretching bands, which show that the presence of alkanes, and at the lower wave numbers, we got the carbon oxygen and carbon hydrogen stretching banding vibration, showing the presence of alkenes in the product. And at the wave numbers lower than 1000, we have CH banding vibration and CH out of plane banding vibrations, showing the presence of alkene and single ring aromatic compounds in the liquid product. These suggest that there was the gasoline scale compounds in the product, which are the heavy waxes, and it is another issue because heavy waxes cannot be used in any direct combustion process. So we can use it as a raw material in refineries and other industries as a fuel, but it also causes the pollution. Okay, then we conducted actually the Then we conducted the Gcms analysis of the liquid product to check what is the carbon chain present in the product, and after that we found that the liquid product contained the gasoline range hydrocarbons ranging from carbon 6 to carbon 12 chain, and some heavy carbons having the carbon chain 13 and higher. So these are the different compounds we find through GCMS analysis in the product. So thereafter, the solid residue, which we assume that it is a carbon nanotubes, we perform the XRD analysis of the residue, and we observe the peaks at 2 theta of 25.8 degree and 26.2 degree and 26.1 degree. And the corresponding plane was 002, which shows that these were the multi-walled carbon nanotubes. Some other peaks in the XRD analysis were also observed, which may be the amorphous carbon due to the amorphous carbon or due to the catalyst or the heat sector itself. Okay, then we perform the STEM analysis of the residue to check further that either these are the carbon nanotubes, and if the carbon nanotubes, these are the single walled or multi-walled carbon nanotubes. So the image A was the residue produced with the HDPE, the image B was produced with PP, and the image C was produced the mixture of these two. And we can see that in these images, the C shows that the tube structure is much better as compared to the A and B, and the diameter is also in controlled range. The amorphous or the impurity content of the product is always low, is also low as compared to the first two images. And in first case, we produced high gas and the high liquid and residue, But we also see that HDPE in image A also produce amorphous products, and this is due to the high amount of the residue. It means that the reaction was not fully complete, was complete, and some residue in the form of the catalyst, amorphous carbon, or the heat susceptor was there in the structure of carbon nanotubes. In PP case, we see that the solar residue was small, but the impurity was also small as compared to the case one, and the impurity level reduced further, and structure of the carbon nanotubes improved when we mix these two. It shows that when we mix two feedstocks, the hydrogen production remain almost same, but the amount of the carbon nanotube decrease over time, and quality improves with the time. So here are some conclusions of our work. The main products are gasoline range liquid fuel, including and hydrogen and carbon nanotubes, especially the multi-walled carbon nanotubes. And FTIR profile shows that carbon-hydrogen bonding of alkanes, alkenes, and alkyne groups in the liquid product. The highest efficiency of hydrogen gas was 126.9 millimolar per gram, which is reasonable as compared to photocatalysis or other methods. Gcms analysis shows the presence of the carbon 6 to carbon 12 and some heavy hydrocarbons with carbon chain 13 and plus. The PP produced highest gas yield, while HDP produced highest oil and CNT yield, but the mixture of these two produced the small hydrogen and the liquid, but the solid product was more structured as compared to first two cases. The solar residues was identified as multi-wall carbon nanotubes with outer diameter of 30 nanometer to 93 nanometers. And the STEM analysis of CNT illustrated the tubular-like structural morphology of carbon nanotubes, having some impurity particles in the structures, which can be removed by proper tuning of the pyrolysis parameters, as well as by selecting suitable catalyst and the heat susceptor. So optimization of the process can result in well-structured carbon nanotubes, which have tremendous future in nanotechnology and also in the material science and in medical sciences. So especially in engineering and aeronautical industry. So thank you very much.
Thank you very much, Dr. Yasin, for sharing very innovative carbon nanotube works with us. Room is open for questions. Okay, thank you again, Dr. Yasin. Now we will move to our next session, which is a poster session. The PhD students and MS students are involved in this poster session. From PhD, we have two students, Ms. Hina Imtiaz and Ms. Zainab Bashir. And for MS, we have 5 students, Ms. Sara Ijaz, Ms. Amara Arshad, Ms. Asar Abdasad, Ms. Zebun Nisa, and Ms. Khadia Irfan. So now we will see the poster session.
Optical and dielectric applications. So the abstract of my poster is Partisanite was prepared using non-stoichiometric composition by solid-state method at 1200 degrees centigrade. Structural analysis revealed that Partisanite is a major phase and Bilastronite is a minor phase with no other impurity. Morphological analysis revealed the irregular morphology with particle size 323 micrometer. The optical band gap ranges from 4.48 to 5.0 electron volt, suitable for sensors, bolometer, and optical electronic applications. Dielectric constant from 3.4 to 7.7, resistivity from 2.6 to 10 to -8 to 4.5 10 to -7. AC conductivity were found at 2.1 to 3.8 Simon per meter, making it suitable for low temperature coal-fired applications. So if we talk about the introduction of Partisanite is a tetragonal structured element. In 1953, Broken Hill Associates smelters at Pure, South Australia, described calcium zinc silicon oxides from slag furnaces. So, Partisanite is a rare calcium-rich developed by incorporating zinc into calcium silicon oxide system to enhance its chemical stability for applications. So, it is a ternary compound, always have liquid tension in the biomedical field because of its better biocompatibility, chemical stability, bending strength, and structure toughness in bone regeneration. So the aim of my research, as it has a frequent tension in a medical field before, but there is no any evidence to calculate its optical and dielectric properties, which I have done in my research. So if we talk about the structure of Partisanite was obtained by calculating lattice parameter. It had a tetragonal structure and P421 space flow. In this structure, a heterocyclic 5-member tetrahedral ring is formed by linked zinc silicon tetrahedral. The rings connected to create a conjoined sheet parallel to C001 and calcium oxide bond hold to the adjacent sheet together. So the methodology of my research for synthesizing Partisanite, I use solid state method used for synthesizing the samples, where I have taken 4 samples with different ratios, calcium, zinc, and silicon oxide, and then pulverized in the mortar and pestle, and then make the pellets under a hydraulic pressure of 7 tons. And then I sintered the pellets at 1200 degrees centigrade for 3 hours at the rate of 25 degrees per minute. So this is the mathematical ratios of chemical composition inside samples, and this is the diagram shows the process of methodology. So now if we talk about result and discussion, the phase analysis of these systems tells us that there has 2 phases existed in the system. First is Partisanite and second is the wollastonite with no other impurity P. So this is the values calculated from the XRD pattern. The trend of the crystal size of the system from top to down, it decreased from the top to down because the concentration of zinc oxide increasing from top to down. We know that zinc oxide is a crystallized resistive material, so that's why we have this trend, and we can clearly see that the Scher formula and WH method have shown the comparative results. So the next technique is the FTIR spectra. FTIR spectra was given in the 2 forms, before sintering and after sintering for the samples. So if we talk about before sintering, there are no show any bands developed in the system, but after sintering at 712 we have we can be attributed to silicon oxide and zinc oxide stretching, which are associated with the formation of Partisanite, which confirm the phase of Partisanite in the sample. The next technique is scanning electron microscopy, which shows that different concentration for the irregular morphology. The average particle size of all the sample was about 323 micrometer, and as we see from first sample to fourth sample, there is a morphology. The whole pattern become less because of the crystallization procedures produced. So the next property is optical properties. We made calculation for 4 values. First is absorption spectra, band gap, or batch energy, and extinction coefficient. So from the first graph, we can see that there is a phase shift of 4 samples. So we have the absorption peak for the system at 213. So it is because the zinc oxide has a good UV absorber. So from the calculations for optical material, we can clearly see that we use this material in antennas and other optical electronic applications. So the next technique is dielectric analysis. Dielectric analysis, we have created three types of calculation for the dielectric properties, tangent laws, AC connectivity to the system. So by the dielectric properties and the tangent laws, we have comparative results. As you can see that dielectric constant and tangent laws are inverse to each other, which shows that the sample 3 has a maximum dielectric graph and AC conductivity and minimum dielectric loss. So we can say that we use this material in the bolometers and capacitors and for LPCC application. The conclusion of my poster is the 4 samples internally were prepared by first method, and by all the results we can conclude that sample 3, sample 1 has maximum AC conductivity and lowest band gap. These properties make it suitable for the capacitor and LTCC application. And this research has been published in July in Optical Materials, which is a W category journal with 3.92 impact factor. So that's all. Thank you.
Assalamu alaikum. I am Zainab Bashir, a PhD scholar from Lahore College for Women University. I am here to present my poster titled Soldier Synthesized Boron Nitride Thin Films for Antibacterial and Magnetic Applications. Novel devices demand new coatings to assure best dimensional accuracy and maximum efficiency. In this research work, boron nitride thin films are deposited by sol gel dip coating using 2 different precursors, boric acid and boron nitrate. Boron nitride is one of the most appealing material from experimental and elemental point of view. It belongs to third nitride family, and at a recent time, its nanostructure has attracted a lot of attention due to its unique properties. The sol gel dip coating technique was used for the preparation of boron nitride thin films. Boric acid and boron nitrate was used as a starting precursor for the synthesis of boron nitride thin film with different molarity. Ammonia was used as a stabilizer. The SEM micrograph of boron nitride thin film deposited on the glass substrate shows that the film substrate is uniform and continuous. The thin film surface is well covered with the distributed spherical grains of varying sizes and diameter around 100 nanometer. XRG pattern shows that the films are polycrystalline and have preferred orientation along 002 plane with direct relationship of the crystallite size with molarity of the precursor. An increase in thickness of thin film is observed for increase in molarity of boric acid, but thickness was decreased with molarity of boron nitrate. UV visible spectroscopy shows that the band gap increased for both precursor with increase in molarity. The films are found to be ferromagnetic with decrease in saturation magnetization for boric acid, and in case of boron nitrate with increase in molarity of both precursors. The electric constant and AC conductivity also decreases with increase in molarity of both precursor. Boron nitride has remarkable antibacterial activity against bacterial strains. Hence, a boron nitride nanostructure can be used to develop biomedical devices protected against bacterial strains and minimize infections. Thank you.
Assalamu alaikum. My name is Zara Ijaz and my roll number is 56. I am an MS student
and my research stopped. I have done my research under the supervision of Dr. Javeen, Department of Physics, Lahore College, Copenhagen University. My topic is to investigate the structural, optical, and dielectric properties of vanadium doped cobalt ferrites by ceramic route method. Introduction: magnetic materials can be soft and hard. Ferrites are hard, brittle, iron-containing mineral that is usually gray or black and polycrystalline in nature. The substances which are spinel ferrites having the general formula Ab2O4, here A and